Hi everyone, today I'll be going through the concept of offline algorithms, i.e. what are they, and more specifically, I'll also be going through the Sweepline technique to solve some problems using offline algorithms. Okay, let's start. Well, first of all, we should ask the question, what are offline algorithms? Well, you might have heard the terms online and offline before, and they relate to how you're given input in a problem. In a problem which is solved in an online fashion, you must answer queries one at a time. So if you have a question where you have to answer a bunch of queries, you have to answer one query before you're given the next query. You don't get the whole input at once. And the opposite of that are offline algorithms, where you're given the entire input at once, and you can pre-process the input however you want, and maybe you can even solve the queries in a different order than they were given to you in the input. And you can do all of that as long as the time complexity is good enough. And yeah, offline algorithms will be the focus of today's video. Okay, let's start with a motivating problem. So first, I'm just going to walk you through what this problem is. So the problem is that we have a weighted undirected graph, and so we're given the full structure of the graph, and we have a bunch of queries. In each query, we're given a node x and a value y, and we're asked how many nodes other than x can be reached from node x using only nodes with weights less than or equal to y. If you didn't understand that, you can go ahead and pause the video and understand it yourself, or I'll walk you through a simple example. So let's say we have some graph like this. The nodes are labeled in the green circles, and edges are also labeled by their weights. And now let's say we're given the following queries. Remember that we're going to be solving this offline, so we require that we are given the entire input before we answer any queries. And in this case, let's say these are our three queries. Now let's consider the first query when x equals 1 and y equals 2. The question is, how many nodes are reachable from node 1 using only edges with weights less than or equal to 2? And if we insert all edges with weights less than or equal to 2, we see that we can also reach node 2 in our graph. So the answer to this query is 1, because there's one node other than node 1 which is reachable. Now let's look at the second query. Again, if we add the same edges in the graph, we see that only node 4 is reachable from node 3. And so the answer to this query is also 1. However, if we look at the third query, when y equals 3, suddenly we're also able to use edges with weight 3. So we're able to use all edges with weights less than or equal to 3. And now we can see that every node in this graph is reachable. So the answer is 4. And yeah, hopefully you understand the problem by now. And let's just try to find some efficient way of solving this problem. For example, the naive solution would do a DFS or BFS for each query, which would have a complexity of O and Q, where N is the number of nodes and Q is the number of queries. Since we have to search the entire graph for each query. So that's kind of inefficient. So let's see how we can utilize the offline property that we're given the entire input at once, and let's see how we can use that to our advantage. Well, okay, how do we solve this? Well, often in DSA, data structures, when we have a data structure problem, we can often make multiple updates and queries to this structure. So a typical problem might have a sequence of different updates and queries which you might have to answer. For example, you don't need to know how this works, but if you have a segment tree, the update could be you have an array and you change the value at one of its values at a certain index, and the query might be the sum of a particular range. And it doesn't matter what the problem is, just know that it's a very common setup that we have multiple updates and queries given to us. And if we have some sort of data structure which can answer these updates or queries really fast, such as a segment tree, then that's usually pretty good. But in our case, we don't have that. In our case, we actually just have a bunch of queries. We don't have any updates. So yeah, we have multiple queries given all at once. And one of the ideas of how to solve this sort of problem offline is we need to transform this sort of problem into our data structure sort of problem. This means that we need to sort of introduce artificial updates to our problem and somehow transform our problem from having just a bunch of queries, and we need to transform that into performing a sequence of queries and updates in some order. So we might note that if we look at the data structure problem, we notice that the answer for each query, the answer of that query is determined solely by the prefix of updates which come before it. So for example, when we are answering this first query, we only care about the 2 updates that come immediately before it. And yeah, this is an important thing to consider, and we'll see in a minute why. The reason why is this is actually very similar to the motivating problem which we were just looking at, because in each query, we only care about some prefix of edges, assuming that our edges are sorted by weight. This means that if we were to take every edge in our graph and sort them in ascending order by our weight, I guess the set of edges which are present in our graph forms some prefix. And this is very similar to what we just mentioned when each query is based on a prefix of updates. And hopefully you can sort of see how you might join the dots, in that we need the edges to sort of be updates. We need our edges to be updates, and we need those updates to be in a certain order. And yeah, since we want some prefix of edges when they're sorted by weight, maybe we should sort our edges first and then perform updates in that order. And in fact, there's a pretty simple solution. Well, we could simply have the update where we add the edge with the next smallest weight, and the query is to find the size of node x's connected component minus 1. Well, what does this really mean? So we are transforming our original problem into a bunch of updates and queries. We haven't figured out what order we're going to do our updates and queries yet, but don't worry. Our update is we insert the edge with the smallest weight that we haven't inserted into our graph yet. And our query is that we find the size of node x's connected component minus 1. The key idea is that when we perform the query, we want the updates that have happened so far, i.e. the prefix of updates before this query, we want those to exactly coincide with the set of edges with weights less than or equal to y. I.e. when we perform a query, we want the updates to have transformed the graph into exactly what we would have if we only had the edges with weights less than or equal to y. Well, first of all, let's just quickly mention some data structure which might be able to handle these updates and queries very fast. Well, our data structure needs to be able to add edges quickly and find the size of a connected component. So if you're familiar with this data structure, we could use a union find data structure, also known as DSU, or disjoint set union. Okay, now let's look at the pseudocode behind this idea, and hopefully it'll make a little bit more sense. Okay, so the pseudocode goes something like this. For each value I, ranging from 1 up to the max weight in that order, where max weight is the maximum weight of any edge or any query in our graph. First, we add all edges with weight I, and then for every query where the y value is equal to I, we will answer that query by looking at the size of x's connected component. This means that, for example, first we add all edges with weight 1, then we answer all queries where we are allowed to explore edges with weight at most 1, then we add all edges with weight 2, and then we answer all queries where we are allowed to use edges with weight at most 2, and so on and so forth. And hopefully you can see that when we're processing a query, the edges that have been added to our graph are exactly the set of edges with weights less than or equal to y, because those are the edges that have been added in earlier iterations, and any edges that haven't been added so far will have weights greater than y. Hopefully you can see that. And so if you didn't understand that argument, I'd recommend that you go back and make sure that you do, because this is a really important idea. Okay, so I'm now assuming that you've understood that idea. Well, this is all good and well, but how do we make sure that this runs fast? In particular, what if the maximum weight in a graph is really, really big? What if we can have edges with weights up to 10 to the power of 18? Now, we certainly can't afford to do this slow iteration, but there's a very simple solution, and that is that we only process values of I which are either present in the graph or is one of the y values of the queries. I.e., if there are no edges with weight equal to 5 and there were no queries where y equals 5, then we might as well skip over 5. We don't even need to test I equals 5. We can skip over it because that won't affect anything. And that means that instead of iterating I from 1 up to the maximum weight, it suffices just to get a set of all values which are either the weight of one of the edges or is the y value of one of the queries. And if we get the set and sort it, we only need to process values of I which are present in this set. And yeah, so we simply loop through all values of I which are in this set when sorted in ascending order. And this is the same algorithm, except we skip iterations where nothing happens. And yeah, because now let's look at the analysis, I guess. Well, how many values of I are we actually testing then? Well, the number of values of I is at most the number of edges in the graph plus the number of queries in the graph, which is m plus q, because, yep, so it's m plus q iterations of I. And then we look at the second part. Well, I guess technically for one iteration of I, it's possible that we do a lot of computation, because it's possible that we have many edges with this particular weight, or many queries where the y value is equal to this particular value as well. So one iteration in itself might take a lot of computation, but we can prove that across all values of I, there is not that much total computation. And that's because each edge is only added once. It's only added in the one iteration corresponding to its weight. And similarly, each query is only answered once, which means that we actually only perform m plus q operations, which are either adding an edge or querying the size of a connected component. And assuming and that means that our time complexity is roughly like n plus q times the inverse Ackermann function of n because of the union find complexity. Yeah, so that would solve our problem very fast. Okay, but maybe this pseudocode, maybe you don't really like getting a set of all possible values. It's a bit fiddly, and I'm about to walk you through an alternative, which I personally prefer, but I think some techniques are better in some circumstances. And the idea is that we kind of want to consider both updates and queries as some kind of event. So basically, what I want to do is I want to take a list of updates and queries. And remember, I'm trying to find an update. I'm trying to find an order to process those updates of adding an edge and querying the size of a connected component. I'm trying to find an ordering of those updates and queries such that I can just transform it directly to what we wanted previously, where we had the data structure where we just made a sequence of queries and updates. And so what we want to do is we want to treat both updates and queries as different types of events, but we kind of want to sort both the queries and the updates together. Yeah, so we want to sort all of the events so we can just process this list of updates and queries. And it makes sense that we just sort each event, we just sort the events by the total edge weight. And that means that if for example, if a query, like a query with y equals 3 will be before an update with weight 4, because that is the sorting of our events. We're sorting the events in ascending order by values. And yeah, hopefully this idea makes sense to you. We're basically just sorting the updates and queries together. If you've watched some of my screencasts, you might see me do this in some of my LeetCode contests as well. And this works because, yeah, it works for the same reason. Every time we process a query, the updates that have happened so far are exactly the updates with values less than or equal to our current queried value because of our sorting. And there's only one thing that we need to think about, is that how do we tie break events with the same edge weight? I.e., if we have an update adding an edge with weight 4, and we have a query where y equals 4, which one should we prioritize? Which one should come first in this ordering? And I recommend that you just think about this a little bit. And if you think about it, a query where y equals 4, you want to have added the edge with weight 4. And that means that we should put updates before queries of the same edge weight. So that's our tie break in our sorting function. Now we can do variations on these events, and this is why I like thinking about it in terms of events. It's easy to make simple modifications. So for example, if we wanted our query to only consider all edges strictly less than our y value, we would reverse the tie break and we would put queries before updates of the same edge weight. If instead in our query we wanted to consider all edges greater than or equal to the y value instead of less than or equal to, then we kind of just reverse sort. We would sort everything in descending order. So it's easy to make simple modifications to get different results. And I hope that you have the intuition to be able to figure out which sorting comparator that we need. All we have to make sure is that when we just try to remember, when we're processing a query, the updates that come before it should be the ones that we want to consider. Okay, now let's first of all, let's just look at a little challenge. So that was an offline algorithm to our motivating problem about graphs and edge weights, but I want you to try to find an online solution. That means that you have to answer queries one at a time. You aren't given the whole input at once. And I mean, you still get given the graph beforehand, so you can pre-process the graph, but each query should be answered independently, and you can't do any of this offline algorithm stuff. So I challenge you to find an online solution that runs in a complexity better than just doing a BFS or DFS for each query. And I guess if you have a solution, you can leave it in the comments, and then maybe I'll respond and tell you whether you're correct or not. Okay, now let's look at a slightly different problem. This is probably the most famous in terms of the Sweepline, the terminology for the Sweepline technique. And the problem goes like this. We have a bunch of inclusive intervals. For example, the inclusive interval 3, 7 means all integers in the range between 3 and 7 are inclusive. And we have a bunch of queries, and the query is, we're given an integer x, and we just need to answer how many of the given intervals contain the integer x. So here's an example list of some queries and some intervals, and I'll just go through one of the queries for you. For example, when x equals 4, well, we can see that the first 3 intervals all contain the integer 4, because 4 is between 1 and 5, it's between 2 and 4, and it's between 3 and 7. However, it is not between 9 and 12, so the answer to this query would be 3, because there are 3 given intervals which contain the value 4. Now, again, we're going to solve this offline, so we're going to pretend that we have the whole input at once, and we can answer the queries out of order. Now, here is a visual representation of the previous example. So I've used the white line segments to represent the intervals. For example, this topmost white line segment represents the interval 1, 5 because it spans the integers from 1 to 5. And the red dotted lines are indicating queries. So there's a query at x equals 4, x equals 5, x equals 8, and x equals 10. Now, how do we solve this problem? Well, the idea is that we have some sort of sweep line represented by this purple line. We call this purple line a sweep line. And the idea is that we're going to move this purple line through our diagram from left to right. And as this purple line moves, we're going to keep track of the answer. We're going to keep track of the current number of intervals which intersect this sweep line. So let's have a look at it in action. Well, let's start moving the purple line, and we'll look at what happens to this count every time the purple line hits something interesting, whether that be the start of an interval, the end of an interval, or a query. So the purple line moves to the right a bit, and it hits the start of the first interval, which means that we should increment the current number of intervals which intersect our purple sweep line. Now, if we move it to the right a bit more, we can see that as it hits the start of the second interval, we should increment our counter. And same for the third interval, we increment our counter. And if we move it to the right, we see that the purple line reaches the red line. And the red line, remember, represents a query. The query is how many intervals are currently intersecting this red line. But we know that the current number of intervals intersecting our purple line is 3, and the purple line is currently right on top of this red line, which means that the answer to this query is just 3. Now the purple line is just going to keep continuing on its journey, moving from left to right, and we'll just keep maintaining the counts and answering queries along the way. So if we move the purple line to the right a little bit more, we see that as it hits the end point of the second interval, we should decrement our counter because the purple line is no longer passing through the second interval. And if we move it to the right again, we see that it's hit another query, which means that the answer to this query is 2. Now, moving our sweep line to the right a little bit more, we see that it hits the end point of the first interval, so we should decrement our counter. And we do the same for the third interval, we decrement our counter as we hit the end. Now we reach a query, but our counter is 0, so the answer to this query is 0. I'm moving it to the right, it hits the start of an endpoint, incrementing the counter. It hits a query, so the answer is 1, and then we decrement the counter as we hit the end of this endpoint. And now the purple line has reached the right edge of the screen, which means we've done. We've considered all intervals and we've considered all queries, so we are done. And yeah, this is essentially the main idea of the sweepline algorithm. It's most commonly the sweepline algorithm is most commonly when we have some sort of intervals like this, and we sort important. Yeah, we just process how we just keep track of some data structure or some counter as the sweepline moves from left to right. Now, I'm going to try to frame this in terms of events again, because when the sweep line, we only care about when the sweep line hits something interesting. Like if the sweep line is just moving within an interval and nothing's happening, then well, nothing's changing, so we might as well ignore that. So we only care about when something interesting happens to the counter, or maybe we reach a query. So what events do we actually have? Well, we could have that the sweep line reaches the start of an interval, or perhaps the sweep line reaches the end of an interval, or perhaps it reaches a query. These are the 3 types of events which the sweep line stopped at during our previous illustration. And now all we need is some sort of data structure which handles this. And in our case, our data structure is super simple. Our data structure is simply just a counter, a single integer variable, which stores the number of intervals which currently intersect our sweep line. And we can see what we should do. If it reaches the start of the interval, we should just increment our counter. If it reaches the end of the interval, we decrement our counter. And if we reach a query, we just output the counter. The answer to the query is simply just the counter. But this is a simple example where it's just a counter, but there are more complicated examples. For example, let's say we have some problem where we have a bunch of different things, and each thing lives or only exists for a certain period of time. Yeah, so maybe this item only exists between time equals 2 and time equals 6, and we have a bunch of different items, and maybe our queries is some sort of statistic which is computed at a particular time. Then we can do some sort of similar thing where we frame it in terms of intervals. When we reach the start of an interval, that's representing that we need to start considering this item, and we might keep track of some data structure, maybe like a set or something. If we reach a query, we output some sort of statistic with our data structure. And when we reach the end of an interval, that means that this item is going to stop existing and we should remove it from our data structure. So it can be more complicated examples as well. Yep. Anyway, just to summarize, we'll go through a little bit of some of the takeaways, which I hope you've gotten from this video. The first thing is just to be aware of offline algorithms. Check in the input if the question allows you to read all queries at once, and if so, then we can consider using an offline algorithm. And then secondly, we should try to represent our problem in terms of one of the two frameworks which I've just been through. Either we need to frame our problem in terms of a sequence of updates and queries, which we can just perform on a data structure. And importantly, each query needs to be based purely on the prefix of updates that came just before it. So in our case, our update was inserting an edge, and this worked because when we had a query, the updates that came before it were exactly the edges with weights less than or equal to it, which is exactly what we wanted. And yeah, this is common when we have some query where we only care about everything which is greater than or smaller than a given value. And then we can use a similar comparison to the one that we've just walked through. And secondly, we can try to use the more traditional Sweepline algorithm, where we model some sort of property as an interval, and we maintain some Sweepline, and you can imagine visualizing these intervals, drawing them out like I have done, and moving a Sweepline from left to right, and yeah, just looking at what happens when the Sweepline reaches the start of an interval, the end of an interval, or reaches some query. Often this occurs when things exist for a given time period. Now, of course, these two frameworks are equivalent to each other. Like when we process a query in this Sweepline framework, query is based solely on the start and ends of the intervals that came right before it. So in fact, the second and first, both frameworks are sort of equivalent to each other, but I think having different visualizations can help because some of them might stand out to different people. In any case, that's all I have for you for this video. If you would like to see similar content, you should leave a comment below of what sort of algorithm or data structure you would like me to go through. Because as of now, I'm not quite sure. I would like to make more tutorial videos, but I'm not exactly sure what to make them of yet. So if you have anything which you particularly want to learn, then leave a comment below. Anyway, thanks for watching, and I'll see you guys next time. Bye!